Marvin's not here. Ricky is. I guess we could stop right there, couldn't we? And the rest are not here yet. So hopefully they'll be coming. Or at least somebody's coming. Okay, and for some reason, this doesn't recognize anything on here. Okay. Until I go so far as doing this. There, and then it shows up. I don't know why it doesn't show what's on the screen before that. All right. I can't think if there's any questions. It's been a week since we met before. Any questions or anything we've covered so far? I don't know of any major announcements. Where we left off last time was in Chapter 13, Functions of Several Variables, Section 13.7, Tangent Planes and Normal Lines, and we were in the middle of page 932, right at this definition box here. So here's the definitions of the tangent plane and the normal line. If capital F, let capital F be differentiable at some point, capital P, that point is going to be x0, y0, z0, three-dimensional, okay? On surface S, given by f of x, y, z, this function f of x, y, z is equal to 0, such that the gradient of f is not the 0 vector. Now notice, I think we hit the slide before, but we didn't move on from it. This 0 is a scalar 0 because the function is a scalar function. But when you take the gradient of a scalar function, at this point, it can't be the 0 vector. The gradient is a vector, and it can't be the 0 vector. As long as that's the case, then the plane through this point P that is normal to the gradient vector here, meaning perpendicular to that gradient vector, is called the tangent plane to the surface S at the point P. The line through P having the direction of del F, which is the gradient of F at x0, y0, z0, is called the normal line to S at the point P. Now, there's two of them, one going out and one going in, okay? To find an equation for the tangent plane to S, to that surface S, at the point x0, y0, z0, which is point P, let x, y, and z be an arbitrary point on the tangent plane, then the vector v, which is x minus x0i plus y minus y0j plus z minus z0k lies in the tangent plane. Because the point is at that point of intersection, so any x minus x0, which is linear in the x direction, linear in the y direction, and linear in the z direction, has to be in that tangent plane. Okay? So if you know that point, which they usually give you, okay, then the vector that is a vector lying in the tangent plane is just x minus this one, I, y minus that one, j, z minus that one, k. Okay. Because the del F, the gradient of f at x0, y0, 0, is normal to the tangent plane at x0, y0, z0, it must also be orthogonal to every vector in the tangent plane. And you have that del F at x0, y0, z0 dotted with any vector v that's in that plane has to be the 0 vector, which leads into the next theorem. Because you know del F, you've already calculated that. We've just come up with what the v is. So the equation of the tangent plane, if f is differentiable, had to be, remember, at x0, y0, z0, okay? That means it can't have a gradient of 0 there, okay? 0 vector. Then an equation of the tangent plane to the surface given by f of x, y, z equals 0. That is how we define that surface to begin with. at the point x0, 0, y0, z0 would be f sub x, which is your first component here, f sub x at x0, y0, z0. When you dot these two together, that would be dotted with x minus x0 plus f sub y, which is the second component here at that point, dotted with y minus y0, which is the second component here, plus f sub z, which is the third component here at x0, y0, 0, x0, y0, z0, hard to say, dotted with z minus z0, has to be equal to 0 because of the statement here. That description you just gave here is your equation of the tangent plane. Okay, so let's do example 2. And, oh yeah, you were in the last class. We were working outside just about the entire weekend, and between chigger bites and scratches from bramble briars, holly leaves, just about everything else that could scratch me, and maybe even a little bit of poison ivy. Oh, and I had a wasp sting too, okay? Between all that, I'm kind of itching all over, so if I start acting like a chimpanzee up here with fleas, you'll know why. It's not fleas, I don't think. Okay. Find an equation of the tangent plane to the hyperboloid. Whoa, is this a hyperboloid? Let's see. Now, all three squares, so this can't be a paraboloid. One of them would have to be to the first power. All three squared. Two of the signs are the same and one different, so that would have to be hyperboloid. This would be an elliptic hyperboloid, not a parabolic hyperboloid. Can you guarantee it's with one sheet or two sheets? I think it's guaranteed because of that equal 12. Okay. All right. We've just doubled the class size. Way to go. Heaven is here. All right. And I was apologizing before you came in. I'm itching like crazy all over because we worked outside just about the whole 4th of July weekend. And I got chigger bites, maybe some poison ivy, scratches, a wasp sting. I mean, just about everything imaginable. It was great being outside, but now I'm paying the price for it because I'm just itching all over. All right, sorry. So find an equation of the tangent plane to that hyperboloid at the point 1, -1, 4. Well, wait. I have to convince myself this point is on that hyperboloid. Is it? You plug x for 1, that's going to be a -2. -1 for y, that's another -2, so that's going to be -4. 4m for z, that would be 16 minus 4, sure enough, is 12. So that point is on that hyperboloid. Okay? Now, we've confirmed it is hyperboloid and the point is on it. Now we need an equation for the tangent plane to the hyperboloid. Anyone remember how to get that? Say again? I still can't hear. Okay, what do you mean when you're talking three-dimensional derivative? Okay, take partials, that's what you were saying. Okay, in a certain way. Let me go back one thing. Here we have it. Here's the equation of the tangent plane. It's the gradient. That's what I was hoping you were meaning by derivative. And that will give you a vector. We'll dot that with the vector that's in the plane that's perpendicular to this, okay? And that plane at this point, that's your point we just had there, the plane perpendicular to that, perpendicular. A vector perpendicular to that is going to have these components as its the components of x minus x0, y minus y0, and z minus z0 for this, and then this is going to have components of first the partial with respect to x, partial with respect to y, partial with respect to z. So you dot those two together and have them equal 0. Okay. So you're sort of right. Take a derivative, take the partials, but in a very special way. Okay? So that's what we're going to do. Let's first find, let me get my pen set up, the gradient. The gradient of this function f, what's the function f? Okay? We need to sort of back up and do that too. Remember, the surface has to be written this way. F of x, y, z is equal to 0. So basically, our function f is, I'll leave it in this form. No, I'm not. I'm going to change the form because I just like to lead off with positives. Okay? I hope this is okay with you. I'm going to make it 2x squared plus 2y squared minus z squared plus 12 is equal to 0. That's your function. You have to have it equal 0. Okay, so what I did, I moved everything to the right-hand side to make my 2x squared positive, 2y squared positive. That made the z squared negative, but left the 12 positive. That's the thing I'm taking the gradient of. And this will be a vector, that's why I do this. At the point 1, negative 1, 4. Okay? And we also are going to dot this with the vector v, and that vector v is going to be this. Well, let me write that a little bit differently. Okay. The vector v that's in the plane is going to be, at that point, the vector v in the plane tangent at that point is going to be x minus 1 I plus y plus 1 j plus z minus 4 k. That is guaranteed to be a vector in the plane that's tangent to, in that tangent plane. A vector that's in there for any x, y, and z in the plane. Okay? So, what we have to do is find the gradient first. And what is the gradient of that function? Anyone remember how to do that? And here's another thing I'm worried about, folks. I've had this computer on, plugged in, charging since 8:30 this morning. Before 8:30 this morning, I still have a battery that says it's not charged yet. That is not a good sign. I didn't have it on all during the weekend, and it must have run down really, really badly. Okay. But anyway, what's the gradient of that function? Here's your f. What's the gradient? Anyone remember how to do it? A little out of 4x. It's a vector, though. That's going to be the one in the direction of the I vector. Plus 4y in the direction of the j vector. Second. Negative 2z in the direction of the k vector. The 12 doesn't enter the picture at all. Okay, so now we have the gradient, and we have the vector in the plane. So the equation of the tangent plane will be the gradient vector at the point 1, minus 1, 4. dotted with the vector v. I'm just going to write it down again. And we're going to dot these together, and these are going to equal 0. So to dot these, it'll be 4x times x minus 1. And dot products don't have, they're not a vector. It's going to be a scalar. Plus 4y times y plus 1 plus, no, minus, sorry, minus 2z times z, I can't write, z minus 4 equals 0, because the dot product is going to be 0 between those two. So it'll be 4x squared minus 4 plus 4y squared plus, that's minus 4x, sorry. 4x squared minus 4x plus 4y squared plus 4y minus 2z squared minus 4z is equal to 0. Okay. That, to me, is an adequate equation. Okay. Now, what they might do is complete the square. Oh, I haven't plugged in the values. I should have done that earlier, right up here. As soon as I found the gradient, I should have done this. This is going to be 4i minus 4j minus 8k. Because that would have been so much easier to do that. And then, let me erase this. Okay. I didn't need to erase all that, but just a clean sweep, go back and get it done right. Dot this one because it's at that point with v, and we've already plugged in the thing for v, so this will be, where's my v? Bless you. I just erased v, didn't I? Yuck. There it is. It's up there. Okay. So this will be 4 times x minus 1 minus 4 times y plus 1 minus 8 times z minus 4 equals 0. Okay. So it'll be 4x minus 4 minus 4y minus 4 minus 8z plus 32 is equal to 0. Combining things, we get 4x minus 4y minus 8z plus 28, no, 24 is equal to 0. And you could divide everything by 4 and make it x minus y minus 2z plus 6 equals 0. Okay? And that's exactly what they got. X minus y minus 2z plus 6 equals 0. And this was a hyperboloid of 2 sheets, sorry. I stated it incorrectly before. Okay. So the rest, let's just see how they did it. Hopefully it was somewhat similar without the dumb mistake of not plugging in. All right. Begin by writing the equation as a surface, and that's exactly what we did. That's your F right there. Now, they didn't rearrange the order, which is going to come back and bite them, but that's fine with me. Then they consider the that function to be that surface, and then taking the partial of F of, with respect to x, you get minus 4x. With respect to y is minus 4y. With respect to z is 2z. Here we have Jasmine. Increase the class size by 50%. Okay. All right. We're on in chapter 13, functions of several variables, 13.7, tangent planes and normal lines. We're doing a tangent plane problem right now, example 2, top of page 933. We've already done it. We're just seeing how they did it. So they took the partial of each of those, and then they evaluated those partials at the point of intersection, okay, which is 1, -1, 4, which you already confirmed was on the surface, and that would be minus 4 for x, plus 4 for y, the partial with respect of that alpha with respect to y, and h for z, partial of that alpha with respect to z, okay? So the equation of the tangent plane is the f sub x times your x minus 1, which you get from this x minus 1, plus 4, this 4, times y plus 1, which you get y minus 1 is y plus 1, plus 8, that's the partial with respect to z at that point, 8 times z minus 4. Z minus 4 would be that. And set it equal to 0, and that gives us minus 4x plus 4, plus 4y plus 4, plus 8z minus 32 is equal to 0. And then they combine like terms, which is minus 4x plus 4y plus 8z, and then minus 32 plus 8 would be minus 24 equals 0. And what they did, they divided everything by minus 4. We rearranged earlier and didn't have to do that, and got x minus y minus 2z plus 6 is equal to 0. That's the equation of the tangent plane. Okay. Now, this figure shows a portion of the hyperboloid. This would be an elliptic hyperboloid of 2 sheets, and they don't show the bottom sheet. But here's the point. 1 on, here's x. 1 on x, minus 1 on y, and plus 4. 1, 2, 3, 4 on z. That looks about right. Plane's going like that. It's just really hard to see on a two-dimensional plane, trying to draw the three-dimensional thing, what the orientation here is. But the y, the z, has a very positive slope, 8, the gradient vector. The other two is minus 6 on x, minus 4 on x, which is going that way on x, and it's really hard to see here, and plus 4 on y. And I have a feeling, it's just hard to see. I have a feeling they should have switched around like we did, because we had 4 minus 4 minus 8, and that looks more reasonable than what they've got. But anyway, this is a portion of the hyperboloid, and the tangent plane at that point, it touches at that point, doesn't touch anywhere else, but it has those characteristics. drawing that plane is not an easy thing to do either. So it's going out on x1 for every one, it's going backward on y, and then downward on z. So sure enough, it is seems to be following that. One positive on x, negative on y, and down 2 on z. That sure seems like that. Describes that plane pretty well. All right. Any questions on that? If you follow the pattern, it makes a lot of sense. Okay? Just remembering the pattern. All right. Now, to find the equation of a tangent plane at a point on a surface given by z is equal to f of xy, you can define the function f by f of xyz is equal to f of xy minus z. Or z minus f of xy. It doesn't matter. I usually prefer it this way. Then s is given by the level surface, f of xyz is equal to 0. And by theorem 1313, which we had just earlier, an equation of the tangent plane to s at the point x0, y0, z0 would be the partial of f with respect to x at this point here, dotted with the vector in the tangent plane, which would be x minus x0. So there that is. This is the... Now, wait a minute. Yeah, okay. Written this way, all your xy components are still here. Z component is there by itself, okay? So the partial of this f with respect to x is the same as the partial of this f with respect to x. So that's why they changed it from capital F to little f here at x0, y0, because this is only a function of two variables times x minus x0, plus partial of f, this little f with respect to y at x0, y0 times y minus y0. There it is, y minus y0, minus the partial of z with respect to z, which is 1, okay? So you don't have a separate partial here, times z minus z0, and that's equal to 0 because they're perpendicular. This isn't because this is equal to 0, it's because the tangent plane and the gradient vector are perpendicular. That's why the dot product is 0. Okay? So that gives us a little bit simpler formula, if you can remember to put it in place there. Now, with that in mind, they didn't give us the example, did they? Let me see if I can find this. I didn't turn the page, that's why I can't find it. Well, no, this was at the bottom of that page. So example 3, 4, and 5 are missing. So let's go back and do those before we get to the angle of inclination. All right. Clear my screen here. Sorry. Ate a granola bar in between classes. I crammed it down because it was running out of time. And I think I swallowed something the wrong way, so I'm coughing like crazy. Find an equation of the tangent plane to the paraboloid. Here's the paraboloid. Z is equal to 1 minus 1 over 10 times x squared plus 4y squared. Okay? Find an equation of the tangent plane to the paraboloid at the point 1, 1, 1 half. Okay. Now before I get carried away anywhere, let me make sure of one thing. I want to make sure this point is indeed on this plane, on this shape, this parabola. Okay, when x is equal to 1, this is going to be minus 1/10. When y is equal to 1, that's going to be minus 4/10. So those added together are going to be minus 5/10. Well, this will be minus 5/10. And 1 minus 5/10, which is 1/2, is going to be 1/2, and sure enough, that's what Z is. So yeah, that fits. That's on there. Okay. Now, we have, and by the way, this is a paraboloid because you have the Z is equal to, it is to the first power, and the X's and Y's to the second power. This basically is almost describing an ellipse, so this is an elliptic paraboloid. And here's a Z over here, so this is, going to be a shape like this. Now, I would say this one's going to be opening downward because the minuses with that, okay? So, can't swear to that, but I believe that'll be the case, that this will be opening downward. We'll see when it comes up. The 1/10 here basically is saying to me this is spread out like this, spreading pretty rapidly because, okay, did I say that right? Yeah, because the Z is going up pretty slowly because when this goes up any unit, Z is going up 1/10 of that. So, yeah, Z is expanding slowly, so this is opening really widely down here. Okay, that's my description of it. Now, how do we find, and what did they ask for? An equation of the tangent plane to that paraboloid. What are we going to have to do? Okay. What we want to do is do the partials in a sense of kind of the gradient thing. And like we saw before in that last example, the gradient of this, now it really helps to get them all on the same side, okay? And I think that's what they did before. Let me make sure they did. Yeah. You write your capital F function as your little f, which is everything on the right here, I'm going to move it all to the other side. I'm going to make this 1/10 x squared plus 4y squared plus z minus 1, because you want that equal to 0. Okay? I just don't like messing around with as many negative signs because they tend to trip you up. You move that to this side and then bring the 1 over, that makes it negative. Now, the gradient of this function f, and we're later going to do it at the point 1, 1, 1/2, but right now we're just going to do it x, y, z for now. So let's do that. What would that be? Like you say, take your partials. Say again? It's 2 times 1/10 is 1/5 x in the I direction. I don't know how the j came out there. Continue. Plus 8/10, which is 4/5, right? 4/5, I can't write, or 0.8 you could have said. 0.8 y in the j direction. Okay, it's just plus, the partial with respect to z is 1, so that would be plus k. Okay, so there's the gradient. Now, a representative line in the tangent plane that goes through this point here is going to be the vector v. This vector in that plane is going to be x minus 1 I plus y minus 1 j plus z minus 1/2 k. You just put these values in as your x0, y0. Oh, this is itching me like crazy, and the more I scratch it, the worse it itches. I forget about it. Just do it automatically. So there's your vector in the tangent plane. Okay? Now what we're going to do is dot this with that, but let's go and fill in this value. Okay? We know this is 1/5 of 1, so it's 1/5 I plus and 1/5, 4/5 of 1 is 4/5 j plus k. Because remember, there was no z there, so there's nothing to fill in. When you take the partial, it's just k. That's it. So we're going to dot these two vectors together and set it equal to 0. So that's 1/5 of x minus 1 plus 4/5 of y minus 1 plus z minus 1/2 is equal to 0. Just want to scratch. Okay. So what I'm going to do right off the top, multiply everything by 10 so I get rid of my denominators. I've got to remember I did that. Okay? So 10 times this will give me 2x minus 2, and 10 times this is going to be plus 4y minus 8 plus 10z minus 5 is equal to 0. Now, I just did that so I wouldn't have fractions. Not that I mind fractions, but they're just messy. Now, I hope I got everything multiplied right. I think I did. So let's combine these together. 2x plus 4y plus 10z. And now we've got minus 10 minus 15 is equal to 0. Nothing will divide out, so I'm going to be happy with it in that expression. I wouldn't mind to put the 15 on the other side. If they want to do that, they certainly can. They didn't do this. They left it as with fractions in there, minus, and they put minuses in there, minus 1/5 x minus 4/5 y, I don't think I have that right, minus z plus 3/2 equals 0. Now I think I messed up somewhere here. Right here is where it was. I'll multiply by 10. That made me 2x minus 2. That should be an 8y. I got the second one, but not the first one. 8y minus a plus 7. So that gives me an 8y here. Okay. Still nothing I can divide by to make it simpler, but they left it in fifths. So leaving it in fifths, dividing everything by 10 which undoes what we just did, is 1/5 x plus 4/5 y. Say 4/5 y and put 4 over y. Okay. My hand's moving faster than my mouth. 4/5 y divided by, that would be plus z minus 3/2 is equal to 0. Now that's one way to express it. They did it with the minuses. Minus 1/5 x minus 4/5 y minus z plus 3/2 equals 0. Either way, it's going to be the same. All right. And then one other little comment here. The gradient del f, or grad f, of x, y, z provides a convenient way to find the equations of normal lines, and that's what we're going to be doing in example 4. Now notice we didn't say anything about normal lines in any of the other, oh, I'm sorry, they did too. Let me scroll backwards and point that out to you. That's the equation of the tangent plane, but it was here. The normal line, the line through P having the direction of del F, so notice its coefficient is going to be exactly what del F is. It's called the normal line to S at P. Okay? So that's why they say, knowing the gradient, you're going to know the normal line. So let's go back to where we were. Can I erase this? Okay? All right. Oops, I'm on the wrong page. Example 4. Now this one you can go to larsoncalculus.com for an interactive version of this type of an example. Okay, it says find a set of symmetric equations for the normal line to the surface. Here's our surface. Different from before. X, Y, Z is equal to 12. At the point 2, -2, 3. No, -3. Goodness gracious. Getting a headache. I'm not sure why. Maybe I haven't eaten enough today. I don't know. Okay. Now, there's our equation. There's our surface. X, Y, Z is equal to 12. Now let's just make sure this point is on that curve. X equal 2, Y is equal to -2. That's going to be -4 times a -3 will be a +12. Yes, it's on that curve. Okay? It's going to be 2 on the x-axis, -2 on the y-axis, and -3 on the z-axis. So somewhere down here. And that's sure what they show here. They just orient it a bit differently. Okay? Now, we want to make sure this is in the form of f. So your capital F as a function of x, y, and z is going to be x, y, z minus 12 is equal to 0. Okay? Now, what are we going to do next? Hint, the gradient provides a convenient way to find the equations of the normal line. So it says find a set of symmetric equations for the normal line to the surface at that point. So what might we do? Take the partials. In other words, find the gradient. That's the best way to say this. The gradient of f, and that's going to be a vector, at x, y, z is equal to what? I can't hear. What was the question? we hope the gradient is not 0, because if it was, you can't do this, okay? Because that means you have a horizontal tangent plane, and your equations don't work well there. Here's your function. What were we doing before?
Taking a partial in respect to x.
Right, and what would that be?
So there's 1?
No. Remember, you treat, when you're taking the partial with respect to x, you treat the yz as if they're constants.
So yz.
Yeah, yz. So that would be yz in the I direction, because f sub x goes there. Next. And not minus. Plus. That's xyz. Minus 12. That's just a constant. When you take the, take the partial of that is 0. Okay. Plus. Is what?
J.
Yeah, what is the j component? The partial of this thing with respect to y. And that would be, second, x, z, y, j, plus, right, x, y, k, okay, and that's, that is your gradient of f. Okay, now what we want to do is do that gradient of f at 2, -2, -3, at that point. And what will that be?
So
6i minus 6j minus 4k. Okay. Now, we're not finding the tangent plane. We're looking for the set of symmetric equations for the normal line to the surface. Okay? Now, let's again go back here. The line through P having the direction of del F is called the normal line to S at P. So having the direction of that, that means that we're going to be have those same coefficients. Okay? So that means your normal line at that point has direction numbers 6 minus 6 minus 4. So here's how you write that. Now, this goes back to something we did, I think back in chapter 11, but I can't remember for sure what the chapter number was. And it's the normal line is x, and by the way, they say symmetric equations, and they mention those there too. X minus 2 over 6 is equal to y plus 2 over 6 is equal to z minus 4, no, plus 4, no, getting all crossed up here, z plus 3, I was looking at the wrong thing, over four. Okay. Only it's a minus 4. These two are minuses because of those two minuses. That one's a plus because of that one. Okay? Now they put the minuses in the denominator. I don't really see why, but that is your what they call set of symmetric equations for the normal line to the surface. Okay. Now they refer to the figure here, and since I really don't want to draw the figure, I'm going to hold it up for you to see. It doesn't make the normal line make any more sense, but hopefully it will, okay? A little bit, anyway. All right. Here's our surface here. Actually, it's two parts of sort of hyperboloid-looking structures there, okay? It's off at an angle because these are multiplied together. That shifts your axis badly. And the point at 2, -2, 3, here's the x-axis here, so you come out 2 here, go back on the y -2, and down -3 for your z, and that brings you to this point here. Now, to me, that looks like they're way too low, but we'll let them get away with that. Okay, the gradient vector is the direction perpendicular to that, the tangent plane there, and it points usually toward the interior of that surface. So it's pointing there, and that was the gradient at -2, -3, +2 on x, -2 on y, and -3 on z. And you see that's heading in that, well, no. Okay. The gradient there is 6i minus 6j minus 4k. So 6i, that's going to be out this way 6 units, down -6 units in j, and then down 4 units on the k. So that looks rather reasonable, okay? Now, your normal, and I can't hold it up any longer, you get from the line itself, x -2, y +2, z +3. Those go there. And then your, what they call direction numbers, +6 here, -6 there, -4 there. I just brought the negatives up and put them in front. It doesn't have to have them down there. So that's really all we had to do was find, this is what they call a set of symmetric equations for the normal line to the surface. And these symmetric equations, those are your parametric equations for the x, y, and z, basically. Okay. That's hard to help. Okay, to move to example 6 or 5. Were there any more questions on that? Okay. Example 5, find the equation of a tangent line to a curve. Find a set of parametric equations for the tangent line to the curve of intersection of the ellipsoid. And here's the ellipsoid. X squared plus 2y squared plus 2z squared is equal to 20. All right. First, that is an ellipsoid. All three of these variables are squared, and all of your signs are positive. So that means you have a ellipsoid type structure. If you had divided everything by 20, this would be x squared over 10 plus y squared, x squared over 20, y squared over 10, z squared over 10 is equal to 1. and that would have meant the square root of 20 is your x-axis, so that's your, I have a name for it. I want to say primary, that's not quite it. Major axis is the x, and the y's and z's are equal at square root of 10. Something a little over 3, this one be a little over 4. Okay? So that is an ellipsoid. So we verified that, or at least talked about it. So find a set of parametric equations for the tangent line to the curve of the intersection of this ellipsoid and the paraboloid. And the paraboloid is x squared plus y squared plus z is equal to 4. Okay? Now, why is that a paraboloid? Well, because these two are squared, but this is to the first power. So these two form a parabola, those two form a parabola, and this is an elliptic paraboloid because those two form actually a circle, which is a special case for an ellipse. Okay? When you wipe out the z. That's a 4 there. Okay? Now, so this is a paraboloid, and if you wrote it differently, z is equal to minus x squared minus y squared. That means this paraboloid is opening downward, which we will see in a minute. That's exactly what it's doing. All right, so we want to find a set of parametric equations for the tangent line to the curve of the intersection of that ellipsoid and the paraboloid. Now it says at the point 0, 1, 3. Now what this means is that point needs to be on both of these. So let's verify that it is. When x is 0, that's fine. Y is 1, so this would be 2 plus z squared is 9 times 2 is 18. 2 plus 18 is 20. It's on that one. It's on the ellipsoid. How about this one? 0 plus 1 plus 3 is 4. Sure enough, it's on that. So that point is on the intersection of those two things. Now, what we need to do, find a set of parametric equations for the tangent line to the curve of the intersection of those two things at that point. Now, what seems to me required here is that you need to find the equation of that circle, or whatever it is, the equation of that curve, which is the point of intersection there. The curve of intersection of that paraboloid and ellipsoid. Now, and we know the point where we want that. Now, what that means is these two surfaces have to be equal to each other there. Okay? So what we have to do is write these like this. X squared plus 2y squared plus 2z squared minus 20 is equal to x squared plus y squared plus z minus 4. That means these two have to have points in common. When you do that, notice the x squareds go out. And if you subtract the y squared from both sides, that gives you y squared. Subtract the z squared, oops, you can't do that. Plus 2z squared minus z, sorry. I said z and wrote 4. I don't know what's wrong with the brain here. Minus z I'm going to leave that alone for now. And that will be minus 20 plus 4. So that's going to be minus 16 is equal to 0. I think I've accounted for every term. Yeah. All right. Goodness, I'm feeling rotten. Ugh. All right. Now, why I did that, I wondered if I needed to complete the square here, and I'd rather not if I can get away with it. Let's see. They may not have even done that. Well, they take an interesting bent here. Without worrying about the intersection, which is what I was worrying about, they said, let's first, this is a typical Tevin type thing, let's find the gradients of both surfaces at that point. So let's do the gradient for this one first. What would it be? Well, okay, the gradient of this one. Let me take off the minus because we want that. So what's the gradient of that? Two x in the I direction plus 4y in the j direction Goodness gracious, I can't write. I'm almost feeling dizzy here. Can't get it to erase either. Minus 4z. I couldn't get the pen to write it. Okay. That's K. Sorry about that. Okay, what did you say? Okay. This is the gradient. Let's call this one F. Let's call this one G. Just so we'll keep them apart. So this is the gradient of F. And here's the gradient of G. What would it be? 2x I. Goodness gracious, it keeps popping up there. Plus 2y I. Okay, I mean J. Goodness, I can't get my hands to work right. And then what? I can't hear. K plus K. Whew, goodness gracious. All right. Now, if the two curves have to intersect there, then their gradients must also be the same there. So this will be easier than setting the two curves equal to each other. Set the gradients equal to each other. Okay? And let's just make sure. Oh, they called them X, Y, and Z too. I mean F and G too. 2xi plus 4. Okay. Okay. All right. Now this was at X, Y, and Z. And this was at X, Y, and Z. we want them at this point. So del f, or gradient of f, at 0, 1, 3 would be what? Okay, 0 on the x, so 0i, so we don't have to write that down. What's next? Plus 4j. Goodness gracious, this pen keeps dragging. What was the last? Plus 12k. Okay, let's do the same for g. The gradient of g at 0, 1, 3 okay, you said 2j? Yeah. Okay, just a second. Yeah. I don't need the parentheses, I don't think. That's what I was worried about. I didn't have it before, so let me erase it now. Okay. And then what?
Plus K.
Plus k. Because it didn't have any x, y, or z dependence on it. Okay. And 2j plus k. Got it. All right. Now, the gradient of, say, that ellipsoid, that's going to be pointing either in or out, one way or another, perpendicular to the ellipsoid. For the paraboloid, it's going to be pointing in or out, perpendicular to that. Okay? Now, they're not in the same direction. Okay? So you don't want to set them equal to each other like I was about to think. That can't happen. But what would happen if you do a cross product between those two, then you're going to have a vector that's perpendicular to both of these, and that's going to define the so here's this one, here's that one, say. Something perpendicular to this is going to be in this direction, which has to be the tangent line for that circle. It's going to be perpendicular to those because the tangent line is perpendicular to the gradient of this one, perpendicular gradient of this one. They've got to be the same line, so that's got to be the cross product. So let's do the cross product of, and we've lost both of our I components, so we're basically doing the cross product, of those. So gradient of f cross the gradient of g is equal to, and to do this you do I, j, k, repeat the first two again, I, j. Okay? Goodness, I can't see. All right. I meant to put the... This makes it look like a determinant, but you don't have an odd number of the... I mean, you don't have the different number of columns and rows, but you get the general idea. Okay? Now, let's do the I, j, and k components here. For f, it's 0, 4, and 12. And for, repeat the first two again, 0 and 4. And then for the j, we'll do 0, 2, 1, 0, 2. Okay, so when you do the cross product, if you do this one That gives you, oh boy, 4i 0j 0k 0k plus 24i okay. I lost my place here. Sometimes I like to erase these so that doesn't happen, but that's a 0k, 24i, and I think it's a 24j too. Okay. When you add those together, you get 28i. And that should be the oh, they got minus. I messed up something here. Oh, yep. In the downward direction, it's always negative. Okay. I mean, in the upward direction. So that's a minus 24. So that's a minus 20i. I knew that. Well, I erased too much. Minus 20i. Okay. And that's going to be the cross product, which is the it's going to be tangent to both surfaces. So the tangent line is the intersection of those two surfaces at the point is a line parallel to the x-axis because it's in the minus 20i direction. Okay. Passes through the point 1, 0, 1, 3 because it has to. So the direction numbers are minus 20. I'm sorry, when you factor out the minus 20, the direction number of 1. So a set of parametric equations for the tangent line passing through that point is x equal t, because you're and then y is equal to 1. Okay. It's 0 plus, okay. Okay. That's what I'm going by. The t, the coefficient of t is the coefficient here, 1, minus 0. Okay, so that's just t. For the coefficient for the t in the j component is 0 plus 1, so that would be the 1 there. And then the k component would just be 6. Z is equal to 6. So those are the parametric equations for the line that goes through there. See, the only one that has any dependence is the x, and that's just going to have a slope of 1, you might say, and y is going to be 1, and z is going to be 6. Okay? Oh no, 3. How did I mess up? 3, I don't know where I got 6. That's a 0 down here. Goodness gracious. Z is equal to 3. Okay, again, this is 20 minus 20i. Factor out the minus 20. 1i plus 0k plus 0j plus 0k. So to get your parametric equation, is the coefficient here, 1 times the parameter t plus 0. So that just gives you t. 0 times t, which is 0 plus 1. That's your y. 0 times t, which is 0 plus 3. That's your z. So those are the parametric equations for the line that's tangent to the intersection of those two curves. Okay? So that really brings into your gradients being perpendicular to the surface, both of them, and then the line that's perpendicular to both of those, that's going to be your tangent line. So you had to do a cross product there. Then when you got that formula, factor out any common factors. Of course, the minus 20 is common. It's the only thing that's common. This gives you your direction numbers, 1, 0, 0, and that's what multiplies by your t's. And then you add to it your points from your point in question, which is 0, 1, and 3. So it's going to be 1t plus 0 plus 0t plus 1 for y, and then 0t plus 3 for your z. I want to say component. That isn't quite what you call it. Parametric equation. Okay. Whew. I think it's time for a break. I forgot to mark. Rachel, is it? Yeah. Okay, now. All right. Okay. All right. Well, let's take a quick, if possible, 5-minute break, and we'll pick up when we come back. Everybody got this? It's sort of messy. We'll pick up when we come back with, that was example 5, the angle of inclination of a plane. So let's pause this for a moment. All right, continuing in 13.7, we're now going to talk about the angle of inclination of a plane.
Dr. Allen, good question.
Sure.
Do you want to get our test today or Wednesday?
Let's see. We've only got a couple pages more here, and then we've got extrema of two variables for 13.8. I think it's probably going to be Wednesday, because I'm not sure we're going to get through that all, and we've got a little over an hour left, hour and 15 minutes or something like that. And then application of extrema, I don't think we're going to go over that one. I may do a quick slideshow. And Lagrange multipliers, we're not going to go over that either, except for a quick slideshow. So this is a long, long chapter. But then after that, we're through. So I think that'll probably be Wednesday. Okay. Will you be here Wednesday?
Yes, sir.
Oh, okay, good. I was going to say I could get it to you sooner if you weren't going to be here. I'm sorry. For some reason, it's gotten so dry. It's hard to talk. All right. So the angle of inclination of a plane. That's sort of a weird concept in a sense. Another use of the gradient. Gradients have enormous uses. They are just all over the place. The grad f, gradient of f of x, y, z, is to determine the angle of inclination of the tangent plane to a surface. Okay? Now, I hope this picture will be helpful, but I'm not absolutely certain it will. The angle of inclination of a plane is defined as the angle theta, and theta is always going to be between 0 and pi halves. In other words, between 0 and 90 degrees. Between the given plane and the xy plane. So it's always in reference to the xy plane. If your tangent plane's up here, we reference it to the XY plane, okay? As shown in this figure here, sort of. Just imagine your surface is somewhere here or here, so this is your tangent plane, and then you reference that to here. Well, how you tell? The normal to the XY plane is the k-axis. Got to be, right? XY perpendicular to that is going to be the k-axis. The normal here is going to be that normal vector n that we did a little bit with a couple examples ago. So what's the angle between those? Okay. Now, if you did have a horizontal plane that was parallel to this, then we count that angle as being 0. It's parallel to the XY plane if it's perfectly horizontal. All right. Now, I think I mentioned before, I still haven't charged the battery. I must have wrecked it this weekend by not turning it on. Because the vector k is normal to the xy plane, you can use the formula for the cosine of the angle between two planes to conclude that the angle of inclination of a plane with a normal vector n is this. Now, let's think back. One of the last things they said here, if it's parallel to this, the angle is 0. Okay? Now, that meant for that cosine, if that angle is 0, that meant that cosine had better be 1. Okay? Because cosine of 0 is 1. Well, let's see what we've got here. We've got the dot product between the two, and if those are exactly the two parallel vectors, then the dot product is going to be the maximum between those divided by the magnitude of each of those. So yeah, that makes sense. Well, the k vector is a unit vector, so its magnitude is 1, so it's just divided by the magnitude of n. So that's going to give us the cosine of the angle, then the inverse cosine of this thing will give us the angle. Okay? So, I think we're ready for example 6. Yeah, here we go. Find the angle of inclination of the tangent plane to the ellipsoid. Okay, so this is an ellipsoid. Why? Because each of the variables is squared. All the signs are the same, pluses. So this means it's elliptic in every component. The two co-major axes are your x and y, minor axis being the z. Okay, because these two are the same size. Now, so that's an ellipsoid. They say the tangent plane to this point. Well, let's make sure that point's on there. 2 squared is 4 over 12 plus 4 over 12. So that's 1/3 plus 1/3 plus 1/3. Sure enough is 1. So yeah, that point is on that plane. Okay? So find the angle of inclination of the tangent plane to that curve, to that shape, that surface, that ellipsoid, at the point 2, 2, 1. Okay? Well, the normal vector is going to be in the same direction as what? The line through a point P having the direction of the gradient, good old gradient vector at that point, is called the normal line. So it's going to have the same direction as the gradient. So guess what we're going to do first? Find the gradient. Okay? All right. One more. Here we go. So let's rewrite this. Now, you always really should do this, but it usually doesn't make a lot of difference. The function f is x squared over 12 plus y squared over 12 plus z squared over 3 minus 1 equals 0. You really need to write it that way. And then do the gradient. The gradient of f is equal to what? I can't hear. 1/6 x in the I direction plus 1/6 y in the j direction plus 2/3 z in the k direction. Okay, there's your gradient at any point x, y, z. Okay, we want it at this point. So the gradient of f at 2, 2, 1 is going to be what? 1/3 I plus 1/3 j plus 2/3 k. Okay, so there's the gradient of f at that point. The normal line at that point is going to be in that same direction. Okay, now we can use the gradient as being the normal line. Okay, it's not a unit, but that's okay, but it's in the same direction. Okay, so the angle of inclination would then be, and I can't understand how this keeps getting done, the cosine theta, this is what we just had, cosine theta is equal to the dot product of the normal vector. And it doesn't have to be a unit vector, by the way. This isn't capital N. This is a normal vector, dot k. Now that is a unit vector divided by magnitude of n. So, whoops, wrong way. Cosine theta is equal to the absolute value of n dot, well, let's not even call it n. Let's just go on and call it the gradient vector. Okay? The gradient vector of f dotted with the unit vector k divided by the magnitude of the gradient vector f. Because the magnitude of k is 1. Okay? So, we need to dot those two together. Well, k is 0i plus 0j plus k, right? So that's pretty easy to dot those two, isn't it? What is it? Dot these two. Zero times 1/3 is 0. 0 times 2/3 is 0. That'll just be 2/3 divided by the magnitude of your unit gradient vector, which would be the square root of what? No, square it. My pen has decided to go wonkers on me. It's not printing anymore. There we go. 1/9, you know you square it, right? 1/9 plus 1/9 plus 4/9. Okay? My nose is itching. Okay, so this is 2/3 over, this will be the square root of 6 over 3. Well, the 3's go out, and you basically have 2 over root 6. And if you punch that in the calculator, because the theta is going to be the inverse cosine of 2 over root 6. What do you get? Whoa, wait a minute. They say the square root of 2/3. Is that the same? If you multiply the numerator and the denominator, let's just see. This is root 2 times root 2 over root 2 times root 3. Yeah, that's the same thing. Inverse cosine of 2 over root 6. What do you get? Now, the book gives the answer in degrees, so let's stick with degrees. In other words, be sure you're in degree mode. What you get? What's that? Oh. You might, I think if you turn your phone sideways, don't you get a more expanded calculator with inverse sine and cosine on it? I know mine does that, but I don't know about yours. Does that give it to you? Okay. I think you have to turn it. 35.3 degrees? Yeah. Yeah. Okay, so theta is approximately 35.2 degrees. No, 0.3 degrees, 0.26, which is 0.3 degrees. All right. Now, they show the figure in the book, which I'm not about to graph, or try to even. Okay, here's the ellipsoid at 2 on X, 2 on Y, and 1 on Z. So it's not very far up there, okay? And there's the, yeah, this is almost impossible to tell anything on here. There's the plane that defined by that, okay? The tangent plane. The gradient is perpendicular to that, and I can't hold this much longer. They used 221. Yeah, they just plugged in that. It's interesting how that comes out. But it's 1/3 I, 1/3 J, and 1/3 K. So it's not very far on the I, J, and 2/3 K more up. That looks like it's way too big of a K for what they have for X and Y, but we'll take the word for it. We want the angle in between those two, and that makes it look like a much smaller angle than 35.3 degrees, but it's just because you don't have the perspective you need there. So anyway, that's supposed to be helpful, just let you see, yep, that's what it looks like. But remember, that is always between 0 and 90 degrees, or 0 and pi halves. All right. Well, let's see. They're going to do it, so maybe they'll show the picture. Why was I holding that up? I don't know. So let's see what they got. Begin by letting F be that, we had to rearrange it and set it equal to 0. They didn't even bother doing that. Okay? And then when you take the gradient of that, you get X over 6I, which you got, Y over 6J plus 2/3 K, exactly like you got. Then with those in mind, that is your gradient vector at the point 221. Plug in 2 for x, 2 for y, and 1 for z, and you get 1/3, 1/3, 2/3 exactly. And just let that be, because that is normal to the tangent plane, and k is normal to the other one. It doesn't, let that be your normal vector, okay? Follows that the angle of inclination for the tangent plane is the dot product between those two. Now remember, k is 0, 0, 1, okay? And you're dotting those together, and you're dividing by the magnitude of f, that normal vector alone. And so we'll come back and get that in a minute. But the dot product there is just 2/3. 2/3 times 1 is 2/3. And your denominator is the square root of 1/3 squared plus 1/3 squared plus 2/3 squared, which is 1 ninth plus 1 ninth plus 4 ninths. That's 6 ninths. When you take the square root of that, you get the square root of 6 over 3. And the 2/3, and why they change it to that, I don't know, but it's the same thing. It's the square root of 2 over the square root of 6, which is the same as square root of 2/3. There's nothing magical about square root of 2/3, but they did it. And then the angle theta then is the arc cosine of the square root of 2/3, which is 35.3. So here's that angle, and this is so hard to see anything here. Your point is 2 on x, and you see each one of these bars is 2. 1, 2, 3, 4, 5, 6, no, it's 1. So it's 2 on x, which would be in this far, and then 2 on y, which would be that far, and then up 1 here. So I guess that looks about right. But now you're on this surface, so you can't really see, but the tangent plane is like that on the surface. The gradient there would be your, they don't show the things of that, but that was 1/3, 1/3, 2/3 would be that gradient here. K is like this. The angle in between, the cosine of that would be the dot product between those two divided by the magnitude of your gradient vector, and that's your 2 over root 6, or square root of 2/3. All right. Now, last thing in this section, comparison of the gradients. The gradient of f and the gradient of capital F, little f and capital F, okay? I don't know if this is important to you or not, but they're not going to give you a problem on it until. This section concludes with a comparison of those two gradients. We know that the gradient of a function f of 2 variables is normal to the level curves of f, okay? Because 2 variables, that's going to give you a vector in 2 dimensions, of course. Function that is normal to the level curve. So whatever your level curve is there, it's going to be in that plane. Specifically, Theorem 1312 states that if f is differentiable at x0, y0, and del f is not the 0 vector, the gradient vector is not the 0 vector, then the gradient vector at x0, y0 is normal to the level curve through the point x0, y0. So now that says the gradient 2 is normal to level curves if f is differentiable at x0, y0, that's the function in 2 dimensions, and del f is not the 0 vector, in other words, the gradient vector is not the 0 vector, then the del f, which is the gradient of f at x0, y0, is normal to the level curve through x0, y0. Seems like that's the same thing. Oh, I'm sorry, this is what that's saying, okay? We set it up here, they set it in the theorem down here, okay? Now, so how is that a comparison? Having developed, oh, I'm sorry, they were just repeating. 1312. Okay. I was going to say we've already done that. Okay. Having developed normal lines to the surfaces, we can now extend this result to functions in three variables. The gradient is normal to the level surface. Okay. F is differentiable at x0, y0, z0, and del f is not, the gradient of f is not the zero vector. Okay. Then the gradient of f is normal to the level surface through x0, y0, z0. Okay? Now think again, the normal surface, they have been calling a plane. It doesn't have to be. If this is some fourth dimension here, u, say, or w, or w I guess they usually do, then this represents a surface that's normal to whatever that represents. So that would be normal, the gradient would be normal to that of the surface. Just like the gradient to, in the previous one, 1312, was normal to the level curve, this is normal to the level surface. Okay. And that's finally it for 13.7. Homework exercises here include 3 or 5. They're both at Calc Chat. 5's at Calc View. Any of the odds 7 through 15, they're all at Calc Chat. 7's at Calc View. Any of the odds 17 to 25, they're all at Calc Chat. 19's at Calc View. Any of the odds 27 to 31, they're all at Calc Chat. 27's at Calc View. Either 33 or 35, they're both at Calc Chat. 33's at Calc View. Any of the odds 37 to 41, they're all at Calc Chat. 43's at Calc Chat. 45's at Calc Chat. 47's in Exploring Concepts. You can do that if you want to. It should be at Calc Chat. And then any of the odds that you want to do, 49 through 55, they should all be at Calc Chat. 57 should be at Calc Chat. Any of the odds you want to do, 59 through 63, should be at Calc Chat. Now 63 is a proof if you want to go that route. And then there's a section project with some further information that you might want to look at for a potential paper topic. I'm not sure that would be all that useful. All right, that finishes 13.7. Now we are going to do 13.8, and it's a fairly short section, but we're not going to finish it. Well, wait. There's a chance we could finish it today. If so, I'll go down and make copies. I thought that was a little bit longer section. 13.9, no, I'm sorry. We got 13.8 and 13.9 to go. I'm sorry, we're not going to finish both of those today. Well, we may, I'm not, yeah. We'll figure that out later. Let's do 13.8 now. All right. For some reason, my PowerPoint just blinks out on me, but it's back now. So let's do 13.8. Takes a long time to load. My computer has been running since before 8 o'clock this morning, and I'm still not fully charged the battery. I think my battery is probably dead, if not forgotten. This is pretty poor. Okay, so let's pick up the slideshow from current slide and go from there. All right. Chapter 13 is still functions of several variables, and 13.8 is extrema of functions of two variables. Okay, we're going back to two variables, and I think this whole section is going to be just two variable, and then we're just going to look at applications of extrema. I won't require you to do anything there, and then we'll look at Lagrange multipliers, but you don't have to do anything with that either. So 13.8, extrema of functions with two variables. Now this thing is a three-dimensional thing. two variables down here, third dimension is going to be your dependent variable. Find the absolute and relative extrema of a function of two variables, like we did with single variable calculus. Use the second partials test to find relative extrema of a function of two variables, just like we did the second derivative test in functions of one variable. So let's look at absolute extrema and relative extrema, just like we did absolute max and min extrema and relative extrema in two-dimensional single variable calculus. Consider the continuous function of 2f of two independent variables defined on a closed bounded region R in the xy plane. The values f of AB and f of CD such that f of AB is always going to be less than or equal to f of xy, and that's going to be less than or equal to f of CD. Okay? Now, AB and CD are both in R. Okay? It would help if they showed what they were talking about, but we'll get to that in a minute. For all x, y, and r are called the minimum, okay, and the maximum values in the region. Okay? So here's what they're saying. F of AB is going to be your minimum value if it's less than all the other f of xy's, and f of CD is going to be the maximum value if it's greater than or equal to all the other f of xy's. So in this picture here, it's looking like anyway that these 4 points here look like they're all local minimum, and this one up here is the one local maximum, because none of the other points go as high on the z-axis as this, and it looks like all 4 of these are about the same value on your z-axis here, because it looks like all 4 of those links are the same. Maybe that one's a little shorter. I don't think so. Okay, but anyway, so the region R is here, and these 4 actually are all on the boundary. This one's somewhere not on the boundary. We'll get to that later. But this is called a closed bounded region R. Closed meaning that you count the boundary values. If you didn't, they wouldn't have the minimum. Okay, so you're counting the boundary value here, as well as all the interior points. R contains the points on which f of xy is a maximum, minimum. I think all 4 of those, and the maximum is that one. Okay. Sometimes you only have one minimum, maybe more than one. You may have more than one max, but they have to have exactly the same value. Okay. That's what we mean by local minimum and maximum. Those are absolute, I guess. A region in the plane is closed when it contains all of the boundary points. That's what I was just saying. The extreme value theorem deals with a region in the plane that is both closed and bounded. Okay. Closed meaning it includes the boundary values. Bounded means it doesn't take off and go to infinity anywhere in that positive or negative infinity in that region. The region in the plane is called bounded when it is a subregion of a closed disk in the plane. That's a weird way to say it. A region in the plane is called bounded when it is a subregion of a closed disk in the plane. Okay. Here's theorem 1315. Extreme value theorem. Let f be a continuous function with 2 variables, x and y, 2 independent variables, x and y, defined, and every now and then they have these stupid vertical lines there. I don't know why. It's not in your book, okay, I don't think, okay. On a closed bounded region, R, of the xy plane, there is at least one point in R in which f takes on a minimum value, and at least one point in R where f takes on a maximum value. Okay? That's your extreme value theorem. But again, your f has to be a continuous function, meaning it's not no gaps anywhere. Two independent variables, and defined on both a closed and bounded region. Closed meaning you're counting the boundary. Bounded meaning that it doesn't take off and goes infinity anywhere. Okay. A minimum is called the absolute minimum, and a maximum is also called the absolute maximum. In a single variable calculus, there was a distinction made between absolute extrema and relative extrema. So here's our definition here of relative extrema in two-dimensional calculus, in two independent variable calculus. Let f be a function defined on a region R containing x0, y0. The function f has a relative minimum at that value, x0, y0, if all the f of xy's anywhere close to that x0, y0, anywhere around that, are all greater than or equal to that value, the f at that value, then it's the minimum. For all xy on an open disk, now this doesn't count the boundaries, okay? Open disk that contains x0, y0. If all the other values are greater than or equal to that, then this one's your minimum. The function f is a relative maximum at that point. If your f of xy, all the rest of them in that open disk containing x0, y0 are less than or equal to that, then that's a relative maximum. For all of those in that open disk, that's usually a circular shape, not counting the boundary of it, but just the interior points of it. And x0, y0 is one of those interior points. To say that f has a relative maximum at x0, y0 means the point x0, y0, z0 is at least as high as all nearby points on the region z is equal to f of xy. In other words, the z0 is the maximum of all those z's that you find anywhere nearby points of that x0, y0. Similarly, f has a relative minimum at x0, y0 when x0, y0, z0 is at least as low as all the nearby points on the graph. In other words, the z0 is less than or equal to any of the other z's. Okay. Now, this is a tough thing to look at, perhaps. That obviously is a relative maximum. That looks like maybe an absolute maximum there. Another relative maximum, another relative maximum. I can't even make this one out. Maybe right in there somewhere is a relative maximum. Looks like you're getting close to a relative maximum there. Looks like this may be on the boundary, so you can't really tell. Relative minimum are down in that hole, down in that hole, down in that hole back there somewhere, and down in this one. It's hard to say here because that's on the boundary. I think that relative minimum is there, there. Can't really tell where it is, but somewhere down in the hole here and there. So you get the general idea. Those are the relative extrema. This one happens to look like an absolute maximum, unless that point back here is going up like that. It's hard to tell if any of these is relative, is absolute minimum. That looks pretty deep there, but it's hard to tell. That would be the value down here. This one may actually be even less, but it's hard to tell. You don't count the boundary values when you're talking relative maximum or minimum. Absolute you do, relative you don't. Okay. And actually, the figure in the book may actually be easier to see than that one, a little bit anyway. To locate the relative extrema of f, you investigate the points at which the gradient of f is the zero vector. Just like the first derivative is 0, that is the point to do. Or the points at which one of the partial derivatives does not exist. Now before, it was just a single derivative where it doesn't exist or where it's equal to 0. Now, either one of the partial derivatives may not exist. You investigate that, or where the whole gradient is 0. Such points are called the critical points. The same thing we named them in single variable calculus. So here's your definition of a critical point. I think back then they called them critical values. I like to call them critical points back then too. If f is defined on an open interval R containing some point x0, y0, that point is a critical point of f if one of the following is true. If the partial of f with respect to x at x0, y0 is equal to 0, and the partial of f with respect to y at x0, y0 is 0. Both of them have to be true. Now, for some reason, it looks like that's an O and that's a 0. They're both supposed to be zeros. That was a bad typesetting here. They're correct in the book. On the slide, they made that look like an O and that like a 0. But maybe that should make it. Or, this has to be true. The partial of f with respect to x at x0, y0, or, see, it was an and up here or down here, partial of f with respect to y at x0, y0 does not exist. If either one of those partials doesn't exist, that's a critical point. If both the partials are equal to 0 at the same point, then that's a critical point. Okay. So, if f is differentiable, and the gradient of f at x0, y0 is this, f of x0, y0 I plus f of y, x0, y0 j is 0i plus 0j, then every directional derivative. All right. Glad you're here. Not so very much, but Carlton's here. Okay. All right. Then every directional derivative at x0, y0 must be 0. Every directional derivative. This implies that the function has a horizontal tangent plane at that point, x0, y0. Okay? So if you're up here at that peak, that absolute maximum, or at least a relative maximum of that surface, and your partial with respect to x is 0, and partial with respect to x is 0, partial with respect to y is 0, then you're at a maximum on that surface. Or a minimum on that surface. If you had a valley down there, and this is the deepest point in that valley, then if the partial of f with respect to x is 0, partial of f with respect to y is 0, then that is your tangent plane, and that is a relative minimum. Okay? Now, all this is saying they're critical points now. The picture showed maxima and minimum. They're critical points, but they're not necessarily, these happen to be maximum and minimum, but just because both of those are true doesn't guarantee it is a maximum or minimum. It is a critical point, though. Okay? It appears that such a point is a likely location of relative extremum. This is confirmed here. It sounds just like one of the things you did back in Cal 1. Relative extremum occur only at critical points. Okay? If f has a relative extremum at x0, y0 on an open region of R, then x0, y0 is a critical point of f. And I think they're going to point this out, but I'll point it out first. Just because this is a critical point doesn't guarantee it's a relative extremum. It may be a critical point, but it doesn't have to be. But if it is a relative extremum, it's got to be a critical point. Okay, that's the difference. So here we have example 1. Now, before we move on, there's a picture of a real serious-looking guy there named Carl Weiser-Strauss. Although the extreme value theorem had been used by earlier mathematicians, the first proof to provide a rigorous proof was German mathematician Carl Weiser-Strauss, I think is how you pronounce it. He also provided rigorous justification for many other mathematical results already in common use, where we're indebted to him for much of the logical foundation on which modern calculus is built. But notice this. He was a late 19th century, I mean very late 19th century, well, much of the 19th century. Calculus had been developed 150 years before, but he finally got around to proving many of the things they were using. So, thank you very much. All right. So here's example 1. Now this one's also found at larsoncalculus.com. You could do an interactive version of this type of example. Determine the relative extrema of f of xy is equal to 2x squared plus y squared plus 8x minus 6y. Let me get my pen set up, okay, plus 20, okay? Now, that's your function of x and y. If you put a z out here instead of f of xy, z being the dependent variable, then basically what you have here is a paraboloid, because z would be at the first power and the x and y at the second power. But it would not be a paraboloid centered at the origin. It would be one centered somewhere else. Basically, you have to complete the squares for both of those to find the point of intersection. Guess what? A lot easier to do if you do gradients. You're going to find that local minimum, which we happen to know is a minimum, and you'll have it without having to complete a square. Okay? Thank you. Okay? Makes it easier. So guess what we're going to do first? Anyone want to hazard a guess? What do we usually do first? Second? Yeah, only it's the partial derivative here. F sub x of xy, and what is that? 4x plus 8. That's all, folks. But it must be equal to 0 for it to be a relative extrema, right? Or it doesn't exist. That exists everywhere. So there aren't any values where it's not going to exist, so we're going to do it. So set that equal to 0, and what does that give us? X must be, anyone want to hazard a guess? 4x plus 8 to equal 0, what must be the x value? -2. X equal -2. All right, but we can't just go on that one because this is two-dimensional. We have to do both of the partials. What's the other partial? 2y minus 6, and we set that equal to 0. And what must the y be then? Y is equal to 3. Okay? So, the point where x equal 2 and y is equal 3 must be the point -2, 3. First partial is 0, second partial is 0. So we're going to guess that has the potential. This is your critical point. That's your critical point. Now we have to investigate and see if it indeed is a relative extrema. Okay? Now, so far, we don't know an easy way to do this. Okay? So we are going to have to go back and complete the squares after all. So let's go to our f of xy. Thought we were going to be able to avoid this. Get the x's together. It's 2x squared plus 8x plus y squared minus 6y is equal to notice what I'm doing. I'm leaving some big blanks there. Is equal to minus 20. And here's why I'm doing that. In order to complete the square, first thing we need to do is factor out any coefficient for your quadratic term. So factor out the 2, and that leaves you x squared plus 4x blank plus, and we don't have a coefficient here, so y squared minus 6y blank is equal to minus 20. Haven't changed anything yet, right? Except just factored out the 2x from that term. How do we complete the square there? Does anyone remember the technique? Take half of 4, and that gives you 2. And then you square it, and that gives you a 4. Now, what have we just done? We've just added 8 to this side, right? So we add an 8 over here to compensate. Okay, what do we do here? Half of negative 6 is negative 3. Square it, and that gives you plus 9. So we just added 9 here, so we have to add 9 over here too. Okay? So this gives us 2 times x plus 2 squared plus y minus 3 squared is equal to negative 3. Okay. Now, that also shows when x equals negative 2 and y is equal to positive 3, then that gives us a problem, doesn't it? It says that would equal something messed up here. I don't know what did. All right, I think I've done everything right, and yet I'm getting a different. They're doing it rather strangely in the book, and I don't. We got the same thing, that x equal 2 minus 2 and y is equal to positive 3. That's your, but they've got is greater than 3, and I've got equal to negative 3. if you were to plug in all right, here's where I messed up. Well, I should have left the 20 over here. So let me go back and, whoops. All right. I'm going to leave a blank there still. Okay. The function f of xy is this. Okay. And then they have the plus 20 here. Okay. And what I did was plus 20 minus 8 and minus 9. Okay. And then this would be plus 3. Okay. So there's your function f of xy. Okay. I'll put it on the other side. But you see, we didn't know it was equal to 0. In fact, it probably wasn't. So that's why it wasn't right for me to move it to the other side. All right. Now, for any value you put in x that's different from minus 2, let's just take 0. If you put a 0 in here, then you get 2 times 4 is 8, and that's going to be, plus 3 would be, okay. First put in those values, and you get a 0 here, you get a minus 2 here, that gives you a 0 here, plus 3 here, that gives you that. So this would be 3 on this side, okay? So the value at that point, negative 2, 3, is 3, okay? Now, pick any other point, like 0, 0. That's the easy one, okay? That would be 2 times 4 is 8, plus 9 is 17, plus 3 is 20. That's way more than 3, okay? So this must be a local minimum, a relative minimum, okay? Pick other points around there. Any point you want to pick there, and you're always going to come out with something greater than 3, because this has a value of 3 at that point. This is your critical values, but when you plug that in here, you get negative 2, 3, 3. Any other point anywhere around there, negative 1, 3, you get something greater than 3. Negative 4, 3, you get something, negative 3, 3, you get something greater than 3. Negative 2, 2, negative 2, 4. You'll always get something greater, so this makes this a relative minimum. Okay, so it is a relative extremum. Okay. So let's see how they do it. Okay. Begin by finding the critical points. How do we do that? We take f sub x and get 4x plus 8, exactly like we did, partial with respect to x. Take a partial with respect to y, get 2x minus 6, 2y minus 6. They're all defined for all x and y, so the only critical points will be where both of these are 0. Okay? The first one equals 0, second one equals 0. The point that will be your critical point is negative 2, 3. Okay? By completing the square for f, you can see that for all values other than negative 2, 3, why did it do that? I don't know. Here it comes back. If you plug in any other value than negative 2 and 3, any other value for x other than negative 2, this is going to come out a greater value. At negative 2, this comes out 0. Any other value comes out different from 0, you square it, and it's more than 0. Okay? Any value other than 3 here, 3 will give you a 0 here. Give you any value other than 3 that you put in here. That's going to give you something other than 0. Square that, it's going to be greater than 0. So this, any point you put in here is going to be something greater than 3. Okay? The value at negative 2, 3 will be 3. So this will give you something greater than 3. Any other value you put in there. Without showing you, they just stated that. Okay? So this has to be a relative minimum. Occurs at negative 2, 3. There aren't any places where the first derivative doesn't exist, or the partials don't exist, so therefore this is your only minimum. So it's going to be an absolute minimum. So here it is. Again, I don't like their graphic here too much. It's at negative 2 on x, so you go back to here, positive 3 on y, so there you are at negative 2, 3, and then you go up 3, and that's the value here. Any other value you put in other than those values, any value around here is going to be greater here, so that makes it a relative. And it's a parabola, and we knew that to begin with, so it has to be either going up or down. It's obviously going up. Okay. Relative minimum at negative 2, 3. At the point negative 2, 3, 3. Now, they're skipping example 2, so let's go back and do example 2. I guess we'll do it right here. Okay. Determine the relative extrema of f of xy is equal to 1 minus x squared plus y squared to the 1/3 power. What did we better do first? Anybody? Partial of which? Doesn't matter which, but okay, let's do the partial of x of xy. And what would that be? Okay, you're going to have a negative 2x in it. Guaranteed that. There's another part to it, though. X squared plus y squared to the okay, you're going to have a 1/3 this to the minus 2/3 power. Okay, now I don't know how you like to do the chain rule. How I usually like to do it is minus 1/3 times this thing to the minus 2/3. Then multiply it by the 2x here, and that gives it to you. If you like to do the 2x first, just remember the minus came from out here, the 2x came from in here. That's fine. Then you do the outer part, and the derivative of this would be 1/3 this thing to the minus 2/3 power. Okay. Now I'm going to write that slightly differently. Here's how I'm going to write it. Minus 2x over 3 times the cube root of x squared plus y squared squared. Okay. Now that's a little awkward, but it's a little bit easier to evaluate. Now, the question is, where are the values you investigate? Well, let's go and do the other partial first. Okay? What's your f sub y? It's negative 2/3, same as before. Y times x squared plus y squared to the minus 2/3. Okay? Now, and that written similar to this would be minus 2y over 3 times the cube root of x squared plus y squared squared. Okay. Now my question to you is, what are the points that we're interested in evaluating? What are your critical points? Anyone? And this really comes up with a strange situation. I'm sort of surprised they gave you this as Mr. Second example, but notice they didn't put it in the slide set. Well, obviously, one place is where your first derivative, or your first partial is equal to 0. Well, that's going to be at x equals 0 here, and at y equals 0 there. So here's a critical point, 0, 0. But there's another, and that's where either of your first partials doesn't exist. Well, 3 is always good. Cube roots are always good. But a 0 down here is not good. And where is that equal to 0? At 0, 0. So this is a critical value, a critical point in terms of your first derivative being 0, but it's also where your first derivative doesn't exist. So, and same thing here. Either of these don't exist at 0, 0, but also that's for your, oh man, this is a mess, isn't it? Okay? But the only possible critical value here is, critical point is 0, 0. Okay? So we need to investigate that and see what's happening here. Okay? So now, if you think about this, think about any point other than 0, 0. Let's just say 1, 0. At 1, 0, this will going to be a -2, and this will be, when you square 1, you get 1, square 0, you get 0, cube root of 0, so this will going to be a -2/3. Okay, well, let's back up. Okay, let's get the value of the point here at 0, 0. That's our critical point. So f at 0, 0 is equal to 1 minus 0 squared plus 0 squared is 0. The cube root of 0 is 0. So that's equal to 1. So this point is 0, 0, 1. All right. Now let's think of any point other than 0, 0. Like I said, let's do 1, 0. So this will be a -2 over 3. Because when x equals 1, y is equal to 0, this is going to be cube root of 1, which is 1. Okay? So that's going to be -2/3. Okay? Which is definitely less than 1. So this looks like a relative maximum. Well, let's go to another one. Let's do 0, 1. Okay? And when you did that one, you would have, this would be 0. Oh, I'm sorry. Looking at the wrong thing. Okay, up here. At 0, 1. This is what we should have been evaluating. At 0, 1. Okay? Sorry, I said 1, 0 first. 1 squared plus 0 squared, that would be 1, cube root of 1. 1 minus 1 is 0. So at 1, 0, this is at 0. So that looks like a relative maximum. If you went 0, 1, you get the same answer. Okay? If you do 1, 1, it's even worse. Okay? It's a negative number. And any other number you put in here other than 0, 0 is going to give you something less than 1. Because you start with 1 and subtract something positive from it. So this is going to be a max, a relative max. Okay? Now, the interesting thing here, it indicates you have a plane there, but then your first derivatives aren't defined there. Here's what you have. You have cusps everywhere, okay? And yeah, I can't hold this long, but you see your first derivative doesn't exist in any direction you take it, and yet, so sure enough, this is a local maximum. In fact, it's an absolute maximum for that, okay? It's a maximum of 0, 0. All right. And see if we can move to the second partials test. Okay? To find relative extrema, you need only to examine values of f of xy at the critical points. However, as is true for the function of one variable, the critical points of a function of two variables do not always yield a relative maximum or minimum. I indicated that before. Just because if you have a minimum or maximum, you know you've got a critical point. However, having a critical point doesn't guarantee a minimum or maximum. Some critical points yield what they call saddle points, which are neither relative maximum or relative minimum. Okay? And here's one such example. Here is f of xy is equal to y squared minus x squared. Now, if you think back what this is your z. Z is equal to y squared minus x squared. Well, z is equal to that would be a parabola. Z is equal to that would be a parabola in the other direction. Here, your z would be opening upward on the y-axis, but opening downward on the x-axis. Okay? That is and then when this is equal to 0, that gives you a hyperbola. So this is a hyperbolic paraboloid, because you get parabolas in two direct dimensions and a hyperbola in the other, hyperbolic paraboloid. And remember, this is how they look. And you think of this as a saddle point. Your legs go on either side here, and the horse goes down the middle there. Okay, that's why they call it a saddle point. You're along the x-axis, your parabola are opening downward. In the y-axis, the parabola opening upward. And everywhere else, you have hyperbole. They don't draw the curves on the z. But if you did the z's here, these would be hyperbole like this. And if you did the z's down here, the hyperboles would be like that. Okay? So that is a hyperbolic paraboloid. And that's called the saddle point. Okay? And what you would find, you have a critical point here. The partial of f with respect to x is minus 2x. Set that equals 0, x equals 0. Partial of f with respect to y would be a 2y. S equal to 0 when y is equal to 0. And so 0, 0 would be your critical point. But if you put a point other than 0, 0 in, like 1, 0, this would give you a minus. So you have a negative value going in the x-axis, it'd be going down. If you put a 0, 1 in, you'd have a positive value. So you see, it would not be a minimum or maximum. That's what we call a saddle point. Okay. At the point 0, 0, both partial derivatives are 0. So it makes it a critical value. There's no place where they don't exist. Function f, however, does not have a relative extremum at that point, because on any open disk centered at 0, 0, in the y-axis you're going up, the x-axis you're going down. So it's neither a maximum or a minimum. The function takes on both negative values along the x-axis, positive values along the y-axis. So the point 0, 0, 0, which by the way is the z value there, is a saddle point on the surface. Okay. So, how can you tell whether you got a maximum or minimum? That's where you use your second partials. Let f have continuous second partial derivatives on any open F region containing a point A for which f of x, the f sub x, the partial of f with respect to x at AB is equal to 0, and the partial of y at AB is equal to 0. That makes it a critical point. To test the relative extrema, consider this quantity. It's called the little d, and I can't think that it isn't because it's some sort of a determinant. Okay? Take the second partial of f with respect to x, take the second partial of f with respect to y, multiply those two together at that point AB, same point AB. Subtract from that the mixed partial f sub x, y, and remember if this is a continuous function, continuous second partial derivatives, doesn't matter which order you do that, f sub x, y, or f sub y x, it doesn't matter. But take that value and square it, and if this d is positive, if this product is greater than that squared, then, and f sub xx is greater than 0, meaning it's positive, then that means that this is a relative minimum. Because f of xx is positive, okay, and the product here is greater than that, okay, then that's a relative minimum. If this d is positive, meaning the product of these is greater than that squared, and f sub xx at AB is negative, that means this one has to be negative too, for that product to be greater than that. So then this has to be a relative maximum, okay? But if the d is less than 0, meaning that this one is greater than the product of these two, then AB, alpha of AB, that's the thing, is a saddle point, if this thing is negative. If the test is inconclusive, if d is 0. If this is exactly equal to the product here, if this thing squared is equal to the product there, you can't tell. You don't know if it's a relative maximum, relative minimum, or a saddle point. You just can't tell. Then you have to plug in values and see if you can figure out what's going on. Okay. Makes a difficult situation. So, do we have time for example 3? I'm guessing not. What do you think? What time is it? What's that? 22? Let's see. Can we finish that in 3 minutes? I kind of doubt it. So let's stop and pick up next time at example 3. Okay? Let me give you a few homework exercises here in this section. We just about finished. I think you can do any of the odds, 3 through 7. They're all at Calc Chat. 7's at Calc View. And let's stop there. And after we do the second partials test, example 3, then we'll do the rest of those. Okay, so not too many more there. Okay, so what we'll do next time is we'll finish 13.8. I'll give you your test for chapter 13. I'll also do a quick slideshow of 13.9, okay, and 13.10. It won't take long, okay, just to give you an indication of what some of these other applications are, and then we'll be through with chapter 13 and you can work on your test. The test won't include the last 2 sections. We'll get started in multiple integration, which is kind of undoing partial derivatives, you might think. It's integrating with more than one variable. That's another fairly long section, so it's going to take us most of the rest of the time of the term, I think, to finish 14, but hopefully we'll get some time to spend in 15. Okay? 14 is awfully long. The sections are long, and there's a lot of sections. But 15 is vector analysis. It's a long section, so we'll get as far as we can in 15, and that'll be it for the term. All right. right? Good deal. We'll catch you then on Wednesday. Hey, we're going to have class 2 days this week, not just one. So back to normal.